HighBridge, a division of Recorded Books, presents The Second Age of Computer Science, From Algol Genes to Neural Nets, by Subrata Dasgupta, read by Mike Chamberlain. Publisher's Note: This audiobook contains brief sections of written computer code that is read literally, including punctuation, as it appears on the page. Prologue. P.1. The First Age of Computer Science. In the 1960s, a science the likes of which had never been quite known before came into being. At its epicenter were an idea and an artifact. The idea was automatic computation, the notion that symbol structures representing information about things in the world could be mechanically transformed into other symbol structures representing other pieces of information. The artifact was the digital computer, a machine for effecting such symbol or information processing. And with the naming of this science as computer science, its teachers, researchers, and practitioners chose to call themselves computer scientists. The genesis of computer science has a long and tenuous history reaching back to the first quarter of the 19th century, to pre-Victorian England, in fact. Charles Babbage, with whom the story of the birth of automatic computation properly began, was a product of the Romantic Age in Europe. By the time computer science assumed an identity and a name of its own in the 1960s, its gestation had spanned the long cultural period called the Modern Age, and, indeed, when the science emerged, the world was in the first throes of the postmodern era. At any rate, as the 1960s drew to a close, the discipline was in place. The first batches of formally trained computer scientists were emerging. Universities were offering bachelor's, master's, and doctoral degrees in the discipline. By the end of the decade, computer science could boast a certain level of maturity. It could claim the status of what philosopher of science Thomas Kuhn called, in his seminal book, The Structure of Scientific Revolutions, a scientific paradigm. We may call this the computational paradigm. A seemingly clear representation of this brand new and quite unique paradigm was offered in an influential document defining the contents of computer science circa 1968. Curriculum 68 was a comprehensive report published under the auspices of the Association for Computing Machinery, ACM, founded in 1947, and the world's first professional society dedicated to computing. This document recommended a curriculum for academic programs in computer science, from basic through intermediate to advanced courses. The report was authored by a committee of 12 academics, all drawn from North American universities, 11 American and 1 Canadian, who had solicited and received input and opinions from over 80 consultants and reviewers. It seems fair to say, despite its North American authorship, that publication of Curriculum 68 implied a certain perceived maturity and stability of the computational paradigm as the 60s drew to a close. With historical hindsight, let us call the state of the paradigm circa 1969, reflected in Curriculum 68, as marking the first age of computer science. The subject matter of computer science, according to this report, consisted of 3 major divisions. The first, information structures and processes, concerned the representations and transformations of information structures and with theoretical models for such representations and transformations. It included data structures, programming languages, and models of computation. The second division was named Information Processing Systems and included such topics as computer design and organization, translators and interpreters, and computer and operating systems. The third division, called, somewhat confusingly, methodologies, consisted of broad areas of application of computing which has common structures, processes, and techniques, and included such topics as text processing, information retrieval, artificial intelligence, AI, and numerical mathematics. The message was clear. The basic stuff of the computational paradigm was information. Further support of this idea was given by the formation, in 1960, of the official world body on computing called the International Federation for Information Processing, IFIP. Unfortunately, the term information possesses two quite opposite meanings. Communication engineers use it to mean a commodity devoid of meaning that gets passed around in telephone and other electrical communication systems, rather as money is circulated in financial systems. The unit of meaningless information is the bit, allowing only two values, commonly denoted as 1 and 0. In contrast, in a common sense or everyday connotation, information is an assertion about something in the world. Here, information has semantic content. It is meaningful. The only shared attribute of these oppositional notions of information is that information, meaningless or meaningful, reduces uncertainty. So, which of these connotations was Curriculum 68 referring to when they spoke of information structures and processing, or information processing systems? The report does not explicitly clarify, but judging from the contents of the three major divisions, it would seem that what the authors had in mind was predominantly meaningful or semantic information. So we can say that as the 1960s came to an end, the basic stuff of the computational paradigm was taken to be meaningful information, with the caveat that any piece of meaningful information is ultimately reducible to patterns of meaningless information, that is, patterns of ones and zeros. P.2. Recognizing computer science as a science of the artificial. The authors of Curriculum 68 understood clearly that, despite its originality and strangeness, computer science was not an island of its own. Recognizing that certain branches of mathematics and engineering were related to computer science, they added two other auxiliary divisions of knowledge, calling them mathematical sciences and physical and engineering sciences, respectively. The former included standard topics such as linear algebra, combinatorics, number theory, statistics and probability, and differential equations. The latter consisted almost entirely of topics in electrical and communication engineering. But what Curriculum 68 did not state is what kind of science computer science was conceived to be. How did it differ, for example, from such sciences as physics and chemistry, or from the social sciences such as economics? What, if any, were their commonalities? What was the relationship between the brand new science of computing and the venerable field of mathematics? And what distinguished, if at all, computer science from the traditional engineering sciences? These are meta-scientific questions. They pertain to the essential nature of a science, its ontology, its methods of inquiry, methodology, and the nature of the knowledge it elicits, its epistemology. Every paradigm governing a science includes meta-scientific propositions that collectively articulate the philosophical foundation of the science. If we take Curriculum 68 as a representation of the computational paradigm at the end of the 1960s, then such a meta-scientific foundation was noticeably missing. Yet the founding figures of computer science were very much cognizant of this aspect of their discipline. Largely in defense against skeptics who questioned whether computer science was at all a science, Alan Newell, Alan Perlis, and Herbert Simon, three of the founding faculty of the Computer Science Department in the Carnegie Institute of Technology, later Carnegie Mellon University, published in 1967 a short article in the journal Science titled, "What is Computer Science?" Their answer was, quite baldly, that computer science is the study of computers and their associated phenomena. The disbelievers charged that science deals with natural phenomena, whereas the computer is an artifact, an instrument, and that instruments per se do not have their own sciences. For example, the science underlying the electron microscope is part of physics. In response, Newell and his co-authors maintained that though the computer is an instrument and an artifact, its complexity, richness, and uniqueness set it apart from other instruments, and thus the phenomena surrounding it cannot be adequately parceled out to an existing science. Herbert Simon was a polymath who had already contributed seminally to administrative decision-making, economics, psychology, philosophy of science, and, most pertinently, to the creation of AI, a branch of computer science. Given his particular range of interests, it was almost inevitable that he would want to explore their shared scientific identity and how they differed from or were similar to natural science. The fruits of this exploration was his highly original book, The Sciences of the Artificial, 1969. Here, Simon dwelt on the nature of the artificial world and the things that populate it, artifacts. The artificial world, he pointed out, is to be distinguished from the natural world. The problem that especially intrigued him was how empirical propositions could at all be made about artificial phenomena and subject to corroboration or falsification in the sense that natural scientists construct and test empirical propositions about natural phenomena. In other words, he was arguing for the possibility of the artificial having its own distinct sciences. Thus, computers, being artifacts, the empirical phenomena surrounding them belonged to the artificial world. If Simon's argument is pursued, then we can have an answer to our meta-scientific question. Computer science is a science of the artificial. P.3. Three classes of computational artifacts. If we accept the authors and other contributors to Curriculum 68 as representatives of the first generation of computer scientists, then this generation clearly recognized that the richness of the phenomena surrounding the computer lay in that the computer was not a singular, monolithic artifact, nor was it the only artifact of interest to computer scientists. Rather, there was an astonishing diversity of computational artifacts, artifacts that participate one way or another in information processing and automatic computation. For instance, there was the Turing machine, a mathematical construction embodying the idea of computing, invented in 1936 by the English mathematician and logician Alan Turing at the time of King's College, Cambridge. Turing proposed that any process that naturally or intuitively we think of as computing can be realized by a version of the Turing machine. This proposition was dubbed generously the Turing thesis by American logician Alonzo Church, 1903 to 1995, generously because Church had, about the same time, arrived at a similar proposition using a different kind of argument. And by the end of the 1960s, it was firmly ensconced as a central theoretical element of the computational paradigm. The Turing machine was undoubtedly a computational artifact, but not of the kind most people think of when they use the term artifact. Of a more practical nature was yet another concept, the model of the stored program digital computer conceived in the mid-1940s by a tiny group of pioneers and given voice by the Hungarian-American mathematical genius John von Neumann, and thus often called, unjustly according to some, the von Neumann computer model. Here again is an invention of the human mind, thus an artifact. The Turing machine and the stored program computer model, both abstract entities, are just two of the varieties of computational artifacts that were represented in the computational paradigm as it was at the end of the 1960s, and as reflected in Curriculum 68. In fact, one can place the varieties of computational artifacts into three broad classes. Material artifacts. These are governed by the laws of physics and chemistry. They occupy physical space, and their actions consume physical time. Physical computers and their constituent electronic circuits, input and output devices, and communication networks are the prime examples of material computational artifacts, known, more informally, as hardware. Abstract artifacts. These exist as symbol structures, devoid of any materiality and thus not subject to physico-chemical laws. The Turing machine and the stored program computer model are prime examples of this class, but there are others, such as programming languages and algorithms. Liminal artifacts. These are inherently abstract, yet their manipulation causes changes in material artifacts, such as the transmission of electrical signals across communication paths, changing the physical states of circuits, activating mechanical devices, and so on. They also require a material infrastructure that enables their work to be done. Elsewhere, I have called such artifacts liminal because they straddle, are between and betwixt the purely abstract and the purely material. Computer programs, software, microprograms, firmware, and computer architectures are principal examples of liminal computational artifacts. P.4. The Life and Times of a Paradigm. As Thomas Kuhn pointed out, a scientific paradigm is a dynamic thing. There are holes in its constituent bodies of knowledge that have to be plugged. Controversies must be resolved. Problems suggested by the overall paradigm must be solved. Solutions may have to be revised, even dismissed. The paradigm evolves and grows. An artificial science is driven by the invention of artifacts. New artifacts stimulated by new social, cultural, technological, and economic needs come into being, and older artifacts, no longer of practical relevance, recede into the background or perhaps disappear altogether from scientific consciousness. The new artifacts give rise to new kinds of problems never recognized before. New questions are asked. The new problems engender new ways of thinking. Circumscribing the new artifacts, entirely new bodies of knowledge and philosophies crystallize. They form sub-paradigms. Older bodies of knowledge may be discarded or forgotten, but they never disappear altogether, for one never knows how or when they might become relevant again. Most significantly, however, the fundamental structure of the paradigm does not change. Kuhn, controversially and somewhat disparagingly, called this evolutionary growth of a paradigm normal science because he wanted to distinguish it from radical challenges to an existing paradigm, so radical that they may cause the existing paradigm to be overthrown and replaced by a new one. Thus his terms, extraordinary science and paradigm shift. Thus his description of a scientific revolution. In the Kuhnian framework, normal science and paradigm shifts were the twin pillars of how a science progresses, the one incremental, constructive, and evolutionary, the other iconoclastic, destructive or reconstructive, and revolutionary. P.5. The Second Age of Computer Science. Yet the history of an actual science is rarely as well structured as philosophers of science like to portray. Computer science may well have attained paradigmatic status by the end of the 60s, and there was, no doubt, Kuhnian-style normal science at work thereafter, adding bricks to the edifice created in the preceding decades and enriching the paradigm as a whole. But computer science was still a precociously young science at the time. The computational paradigm was anything but stable. New, unanticipated forces, some technological, some economic, some social, some intellectual, impinged on it. The outcome was that entirely new kinds of problem domains arose over the next 2 decades that both significantly altered existing sub-paradigms and created new ones. In 1 or 2 situations, the core element of the computational paradigm, the von Neumann model of computing, would even be challenged. Indeed, by the beginning of the 1990s, though there was not a paradigm shift in the Kuhnian sense, a revolution, the structure of the computational paradigm looked very different in many important respects from how it was at the end of the 1960s. So much so that it seems entirely reasonable to call the 2 decades from 1970 to 1990 the second age of computer science. My aim in this book is to narrate the story of this second age. So what were the core themes of this new age? P.6. The Quest for Scientificity in Real-World Computing. First, this was a time when many computer scientists became seriously reflexive about their discipline, not so much whether computer science was a genuine science, but about the nature of the science itself. Herbert Simon's notion of the sciences of the artificial mentioned in section P.2, obviously pointed computer scientists in a certain direction. But outside the AI community, Simon being a seminal figure in AI, it is not clear whether the sciences of the artificial had much of an immediate impact on other computer scientists. The intellectual origins of computer science lay in logic and mathematics. As the 1960s ended, the presence of these venerable disciplines was still very much visible in the shape of two branches of computer science. One was numerical analysis, concerned with the approximate numerical solutions of continuous mathematical problems, which was what began the quest for automatic computation in the first place, and that particularly flourished in its first age of computer science. The other was automata theory, concerned with the study of highly abstract mathematical models of computation. For some computer scientists, automata theory was the science in computer science. This suggested, indeed assumed, that computer science was a mathematical science. Research papers, monographs, and textbooks devoted to automata theory were full of axioms, definitions, theorems, corollaries, and proofs in the traditions of mathematics and mathematical logic. The problem was that not all computer scientists were convinced that automata theory had any direct influence on, or relevance in, the design, implementation, and understanding of real computational artifacts. As Maurice Wilkes, one of the pioneers of automatic computing, put it in an informal talk delivered in 1997, one did not need to know automata theory to build physical computers, algorithms, or software. This can be contrasted, he remarked, to the relationship between Maxwell's equations in electromagnetic theory and radio engineering. If one wanted to design a radio antenna, Wilkes said, one had better know something about Maxwell's equations. Automata theory had no such linkages with much of the rest of computer science, including numerical analysis. Moreover, there were substantial parts of the computational paradigm that at the end of the 60s did not seem scientific at all. For example, a substantial part of computer architecture, the branch of computer science concerned with the functional structure and design of computers, was essentially a heuristic, craft-like discipline having little theoretical content at all. So also in the realm of programming, even though there was recognition that this entailed a whole new kind of artifact, liminal in the sense I have used here, deserving a name of its own, software, coined in the mid-1960s, there was a perceptible sense of inadequacy about the way programs and software were being designed and implemented. In 1968, the term software engineering was invented to indicate that software had evolved to a level of complexity that demanded the same kind of intellectual respect that was accorded to the artifacts civil, mechanical, and other contemporary branches of engineering dealt with. Yet it was far from clear what shape this respect should take. Programming languages, abstract artifacts, had reached a more scientifically respectable state by the beginning of the Second Age. In particular, the 60s decade was rich in its advancement of a theory of the syntax of programming languages, concerned with the rules governing grammatically correct forms of programs expressed in programming languages. But semantic considerations, what the elements of a programming language meant and how to characterize their meanings, how language implementers could unambiguously and correctly translate programs in a given language into machine executable code, how programmers could objectively interpret the meanings of language elements in the course of writing programs, were a different matter. Theories of the semantics of programming had indeed emerged in the late 60s, but very little of these theories had been adopted by the designers and implementers of real-world languages and industrial-grade software. Instead, these designers and implementers resorted to natural language and informality in defining the semantics of their programming languages. Collectively, these concerns became audible as sounds of discontent and dissent. They represented a desire for a science of real-world computing that would play the same role in the design, implementation, and understanding of real, utilitarian computational artifacts, as, say, the engineering sciences of strength of materials and fluid mechanics play, respectively, in structural and aeronautical engineering. As we will hear, this quest for scientificity, and how this quest elicited responses, constituted one of the most significant markers of the second age of computer science. P.7. Computing as a human experience. This was also a time when some computer scientists developed a heightened consciousness about computing as a human experience. This, too, did not arise de novo. The makers of the first age of computer science had clearly recognized that although automatic computation with minimal human intervention was their fundamental mission, humans were not thereby absolved of all responsibilities. Having built physical computers, they could not, in the manner of Pontius Pilate, wash their collective hands and look the other way. After all, at the very least, humans had to communicate their intentions to machines. The very first book on programming, authored by Maurice Wilkes, David Wheeler, and Stanley Gill of Cambridge University, was called, significantly, Preparation of Programs for an Electronic Digital Computer, 1951. In Britain, the English spelling of program still prevailed to signify this artifact rather than the American spelling that would eventually be generally adopted. Computer programs, reflecting the user's computational intentions, had to be prepared by human beings. The invention and design of the first programming languages, reaching back to German engineer Konrad Zuse's Plankalkula in 1945, through David Wheeler's invention of an assembly language for the Cambridge EDSAC in 1949, to the development by the American John Backus and his collaborators in IBM of Fortran in 1957, were clear manifestations of the computer pioneers' awareness of incorporating humans into the computing experience. The remarkable transatlantic collaboration leading to the design of the Algol programming language between 1958 and 1963 offered further evidence of this awareness. But with the emergence and development of the computational paradigm in the late 50s, and especially through the 60s, two quite different and contrasting manifestations of the human-computer connection emerged. In both cases, it was not the incorporation of humans into the computing milieu, but rather the opposite, incorporation of computing into the human experience. P.8. Programming as an intellectual activity. Along one front, in the late 1960s, the Dutch mathematician turned humble programmer, as he would style himself, Edsger Dijkstra, articulated a vision of programming as, fundamentally, a human activity. Dijkstra was among the very first advocates of a new mentality, treating programming not only, or not necessarily, as a means for communicating tasks to computers, but as an intellectual activity in its own right, regardless of the presence or absence of physical computers. This mentality can be viewed as a provocative challenge to one of the key ontological assumptions underscoring the prevailing computational paradigm in the first age, that it should concern itself with computing as a mechanical information process, an assumption that, of course, was rooted in Turing's vision of computing. We will hear that although this new human-centered view of programming was rooted in the 1960s, it engendered an intellectual movement in the next 2 decades called structured programming. Human-centeredness formed the second marker of a new age of computer science. P.9. Toward a unified science of intelligence. Neither Dijkstra nor the other makers of the structured programming movement extended their idea of programming as a human activity into the realm of human cognition itself. Envisioning programming as an intellectual activity did not imply that the mind itself was a computational object, a natural computational object, not an artifact. The idea of the mind as a machine has its own incredibly long history reaching back to antiquity. The modern notion of the mind as a computational machine, however, originated in the 1940s, coincident with the time that digital computing was in the air.
Sample complete. Ready to continue?